My name is Zygimantas and I'm a PhD student at the University of Sussex. I'm going to present my work about multimodal fusion of IMUs and EPS body-worn sensors for scratch recognition. First of all, why do we need wearable sensors to detect scratch? As it can be a symptom for mild and benign conditions, this system can be used to identify this disease much earlier and help the user that way. Also, the same system can be used to quantitatively evaluate how much scratching occurs, and this can be directly applied for evaluating the efficacy of a treatment. Basically, if we observe how much scratch occurs before the treatment and after the treatment, we can see the difference and infer how effective the treatment is. Moreover, the same system can be used as a reminder for a treatment, basically during nocturnal scratches when the user is not aware about if he's scratching or not. The system can remind him when it occurs to put on the treatment, and thus the participant will have better sleeps and his skin will be less irritated. So for the dataset collection, we use electric potential sensors, inertial measurement unit, which collects acceleration, rotation, magnetic field, and quaternion data, and 4 IMUs to get the hand coordinates. The EPS uses this integrated circuit to measure the electrostatic charge that builds up. Basically, when the person scratches his hair, static charge builds up and it's observed in the signal. We also use quaternions to get the hand coordinates. As the quaternions encode the general orientation of the IMUs, we can get the XYZ position of the hand by using the average human limbs lengths. So for the dataset collection, we used the participant need to follow a strict protocol, which was shown on the iPad, where they scratched top of head, back of head, side of head, shoulder, and leg. And we collected also a big null class with wash hands, drink water, brush teeth, type to a computer, and walk in the corridor activities, which made our dataset extremely challenging. So overall, we had 6 males, 3 females. Their age were between 22 and 40. We collected 815 scratching instances. The collection time per user was 35 minutes, and total we got 5 hours 15 minutes with a total scratching time of 40 minutes. We used sliding window approach where the window length was 0.4 seconds, and we used statistical features such as mean variance, percentiles, crossing rates, and a frequency-based feature of energy. Then we applied mutual information algorithm to get the 5 best features for each channel, and we fed that directly to the machine learning models KNN and random forest, and we used k-fold cross-validation to see how well it performs on unseen users. We use that to evaluate different permutation of race IMU, hand coordinates, and EPS data, and how they fuse and how that affects the performance. So for coarse activity recognition, the best performance was using hand coordinates of 80.6% F1 score, and with only one device with IMU and EPS, which is 69.8%. Very significant drop, but it's much better than just IMU. For fine activity recognition, the best performance was again achieved with random forest and hand coordinates. It was 66.9% F1 score, and the best performance with one device with IMU and EPS with Canon, 53.4% accuracy. So to sum up, with IMU, which is just one device, we can achieve 63.8% F1 score, of course, scratch detection. With IMU and EPS, which is still one device, we can achieve 70% F1 score with Canon, but for best performance was with hand coordinates, which requires 4 devices, and with random forest of 80.7% F1 score. So fusing EPS data with IMU enabled to achieve higher accuracy and smaller variance between folds, and it also can fit into one device, which means it is as comfortable as Apple Watch. However, the best accuracy was with hand coordinates, which require 4 devices. The setup is uncomfortable, but the dataset was position biased, so that explained the best performance.